Okay, so in this video, we're looking at the expectation or the expected value for different random variables. I'm beginning with the Bernoulli random variable or the Bernoulli distribution. Quickly, a review of what this looked like, and this goes back to our lecture on random variables. Um, you have either a success or a failure, just like two possible outcomes, so either a 0 or a 1, and each of these outcomes is associated with a probability p and 1 minus p, whatever way you want to describe it, right? So the expected value from the definition of expectation or expected value is you multiply the actual x value times the probability value for that outcome, which in this case is 1 minus p, plus 1 times p, which is p. So we can say that a Bernoulli random variable with success probability p has expected value equal to p, right? Or like this is it. Okay, so we know from our knowledge of random variables that multiple Bernoulli outcomes or Bernoulli trials lead to something called a binomial distribution or a binomial random variable. For example, tossing a coin n times, right? And let's say the random variable we are interested in is the number of heads. Okay, so let's look at that. Uh, Maybe let's look at tossing coin again. Easier to relate to, right? N times maybe, and let x be the number of heads, and this is my success, and my success probability is denoted by p, right? So p is success, 1 minus p is failure, right? Let me write down the PDF for this experiment, right? So x of x, I can get 0 heads, I can get 1, 2, I don't know, so on, maybe k, and maybe up to n. So because we are going to write a generalized expression for this particular random variable, right? And just a quick reminder, to get this, we are using the formula for b, k, and p that we derived in the previous lecture, right? So I'm populating that using this. So this is 1 minus p, sorry, that's 1 minus p n, because there are n the coin is tossed n times, and then this is the probability of getting a heads 0 times, right? And then the probability of getting the heads 1 time is np1 minus p n minus 1. And then similarly, this is going to be n choose 2. Remember from the binomial theorem we derived it, p squared, and then 1 minus p n minus 2. For any kth term, it's going to be n choose k. And p of k, 1 minus p n minus k, and so on, up to the final term, which is p of n, right? So now for ease of writing, now I'm interested in the expectation, so I'll have to go and multiply each of these terms and add them up. And so in order to ease my writing of expressions, I'm defining this q, which is failure, right? 1 minus p, right? So now I'm ready to calculate the expectation for my random variable x, which is going to be 0 times 1 minus p n plus 1 times n p1 minus p n minus 1, because I'm simply multiplying x times p of x because that's what the formula says, right? And so on, I can get the kth term as well up to the nth term, right? So in general, I can write this as summation k for any k from 1 up to n, right? K times n choose k, p of k, and q n minus k, right? So this is the general expression for the expected value of a binomial random variable, right? Now we can actually simplify this further, right? So for that, we're using something that's already known to us, that's a lemma. So let me write that down. I can use this information. This is already known to us, right? So this states that, like from our binomial theorem itself, we know that if this is the case, if n is greater than or equal to k and k is greater than or equal to 1, then k times n choose k is actually exactly equal to n times n minus 1, choose k minus 1. You can actually expand the left hand side and the right hand side and prove that. So I'm not doing that here because all I wanted was I required this equality to prove something and then get a standard result, and then this will make our life easier because going forward we can just like plug in the values and calculate the expected value for a binomial random variable, right? So now going back to my original equation from the previous slide, the expected value of x, I'm going to substitute this value there, right? So after substitution, I get this k from 1 up to n times n minus 1, choose k minus 1 times, oops, we go back. Okay, so here it's going to be p of k and then q n minus k. Okay, let me take out the n and the p values, right? Because I can do that. So I'll simplify this further and I'll write it k equals 1 up to n, and this stays as it is, and this stays p of k minus 1. Why? Because 1p came out. And then here I'm again writing it in a slightly different way, although this stays the same. If you look at it, it is the same thing, but I'm writing it in a slightly different way. It's essentially subtracting like 1 from each, right? So now let me assume, just a minute. Let me make sure that we have everything correct. Minus minus, yeah. So 1 will get cancelled here. So that's fine. So let us assume that there is some L that's actually equal to k minus 1. Again, for ease of writing. So my expectation for x will now become n of p, and then L is from 0 to n minus 1, right? Because k minus 1 is L, right? So so this has to change, and then this has to be less than n, 1 less than n, right? So that's that, and then this also has to change because of our substitution. This is n minus 1, choose L, and then p of L, and then q of n minus 1 minus L. So everything I can write down in the form of L. And why did I do that is because I can write everything like this entire expression. I can convert this to something like smaller from binomial theorem. So I'm not describing how, but writing from binomial theorem. So this is a known result, right? So this is the expansion for p plus q and n minus 1, right? Now, I know that I have like only two outcomes, p and q, and the sum of p and q is already known to be 1, right? So whatever it is, I know that, and let me write it down, this is known, p plus q is 1. So therefore, the expectation for this random variable, and by the way, for any binomial random variable, is n times p, right? So the expected number of heads in the experiment of tossing a coin with success probability p is n times p, right? Okay, so this is a standard result. This is something that we should be using in all our problems going forward. Let's look at a quick problem and then move on. So a multiple choice test has 20 questions, each with 5 answers. If you answer randomly, how many questions do you expect to get right? So we have the random variable x, how many questions you get right, right? And you are interested in finding the expectation of x. Now, as long as you can figure out and maybe like write down the assumption here, and not really assumption, but you can actually show that this is a binomial choice because each question is independent and there is a certain probability of success to each trial, right? So this is a binomial, obviously, right? So P is 1 over 5. Why? Because only one out of the 5 options is correct, right? So the expectation is going to be n times P. N is my 20, right? So the expectation is 20 times 1 over 5, which is 4. So you can expect to get 4 questions right in this exam. Okay, so with this, I end this video. In the next video, I'll talk about uniform and exponential.